Good day, everyone. I'm Arvin Enriquez, your subject teacher in General Mathematics. With this video lesson, we're going to discuss representations of an inverse functions under your General Mathematics from Quarter 1, Module 13. Our lesson objective: at the end of this video lesson, you are expected to represent an inverse function through its A. Table of values and B. Graph. Let's deal now with the inverse function defined with table of values and graph. The inverse of a function is a function with domain B and range A, given that the original function has domain A and range B. Meaning to say, whatever your domain in your original function, that will be your range in your inverse function. It's the same thing, no? Whatever your range in your original function, that will be your domain in your inverse function. So we're just swapping our values between your x and y variables, or your domain and your range. So this inverse function of function f is denoted by f of -1, or f raised to -1. So this, we simply use this f raised to -1 to represent your inverse function. It is defined by the equation f raised to -1 of y is equal to x, if and only if we satisfy that f of x is equal to y. In your original function, f of x is equal to y. But the inverse function, once we swap the position of your variable x and y, your f of negative raised to -1 of y is now equal to x for any y in range b. So since both are functions, no? So once we take the inverse function of a one-to-one function, the resulting value must be a function. Then a function has to be one-to-one for its inverse to be a function at the same time. So we really need to check if the given function is a one-to-one function, because only one-to-one function has an inverse function. If it is a many-to-one function, its inverse is one-to-many, which is not a function. That's why we really need to make sure that the values, no, between your domain and range should be one-to-one. There is a one-to-one relationship between your domain and your range. If there is a repetition in your domain, but in your the values, no, in your domain, same thing with your range. So there is no such thing, no, that these values will represent a one-to-one function. There is no repetition of your values in your domain and your range once you are dealing with a one-to-one function. Again, your one-to-one function is the only function that has an inverse function. So in using table of values of the functions, first we need to ascertain that the given function is a one-to-one function. That's why you really need to make sure that the given function is a one-to-one function, wherein no x values are repeated. It's the same thing with your y values, not only for your x value, it's the same thing with your y values, that there is no value or there is no repetition in your y values. It is represented as the x values of the function resulted as the y values of its inverse. It's the swapping of values, no, between your domain and your range once you are dealing with a one-to-one function going to your inverse function. And y values of the function are the x values of its inverse. Oh, so it's the same thing with your y values. Also, the graph should correspond to a one-to-one function by applying the horizontal line test. Not only your horizontal line test, but we really need to make sure that we satisfy both your horizontal and your vertical line test once you're dealing with a one-to-one function. If it passes the test, the corresponding function is a one-to-one. Given the graph of a one-to-one function, the graph of its inverse can be obtained by reflecting the graph about the line y is equal to x. So once we are dealing with this one, you're making 45 degrees with your x, or it's the same thing, no? It's 45. You're making 45 degrees from your y-axis. So again, dealing with this line, so it's an imaginary line wherein it will serve as a mirror, no? Wherein you're going to reflect your original function, no? Your graph of your original function. So whatever the reflection of this graph, that will be the graph of your inverse function. So let's now deal with the example number 1. So in the given function f of x is equal to 2x plus 3 with an inverse function of f raised to negative 1 of x is equal to x minus 3 over 2, no? As discussed in the previous activity or in the previous video lesson. So let us use the x values to complete the table of values in y values for the f of x is equal to 2x plus 3. Now, in this case, no, once we apply the 3 steps, no, so we replace your f of x, we replace your f of x here by simply using your y. Then we can rewrite this one as y is equal to 2x plus 3. Then we take the interchange between your x and y variables, so swapping a position of your x and y variables. Then we're asked to find the value of y in terms of x, so whatever the resulting value there, so that will be the f of negative 1 of x here, which is your x minus 3 over 2. So that will be the resulting value right after we apply your 3 steps, no, in finding the inverse function of the given or in of a an original function, I mean. So here there's a given table here. There's a given values for your f of x. No, this is negative 2. It's not f of x. It's only x. No, it's a typographical error. So your values for x is negative 2, negative 1, 0, 1, and positive 2. And using your original function here, what will be the value of your y if we apply or if we substitute, no, your negative 2 to 2, negative 2 to positive 2 as a value of your x. Now, what will be the value of your y now? So let's try to apply, or we just simply substitute the given values to your variable x. No. Here is the computation. As you can see, the computation here, we just simply apply, no? We just simply apply negative 2 to your original function, which is 2x plus 3. So that will be the value of your x. So negative 2, once we apply to negative 2, multiply by 2 here, plus 3, so that will be equal to negative 1. So meaning say there is a value of y here which is equal to negative 1. Once we apply your negative 1 as a value of your x, then we substitute, no, negative 2 plus 3, it's positive 1, so that's why there is a positive 1 here, as you can see, no? That will be your positive 1, and this will be your negative 1 for your negative 2. And once we apply your 0, so 0 multiplied by 2, that will be 0 plus 3. So your f of 0 now is equal to positive 3. So there is a positive 3 here as a value of your y, if your x is 0. Then next is once we apply your positive 1 to your x variable, then it becomes f of 1. Then 2 multiplied by 1, it's 2 plus 3, it's 5. So there is a positive 5 here, no? If the value of your x is 1, your y is positive 5. Then if x is 2, no? Once we apply your x which is equal to 2 in your original function f of x, then f of 2 now is equal to 2 multiplied by 2 plus 3 is now equal to positive 7. That's why there's a given value here which is equal to positive 7 if x is equal to 2. So this value is equal to your x or your domain values. So this value is your range in your original function. So we can say that this one is your f of x because f of x can be equal to y in your original function. Now, as you can see here, there's a given value of your range, which is your x, negative 2 to positive 2. Then f of x or your y here, which is your range, no? Negative 1, 1, 3, 5, and 7. So let's apply now for us to get the inverse function of this one, no? And let's apply these values. Let's apply the swapping of positions of the values between your domain here and your range here. So thus the table of values where f of x is equal to 2x plus 3 is presented below with its corresponding graph. So as you can see, this will be the complete value for your x and y. So it's a typographical error. It's simply your x value. Then this one will be your f of x, or simply your y value or your range. These upper values, no, the values in your upper part of your table, this will be your domain or your x values. And the lower, the values in your lower part of your table is your range or your y value or your f of x. Now let's try to plot this one, no? Once we apply your negative 2 and negative 1, your point will be here at some point here, negative 2 and negative 1. Negative 1 and positive 1 will fall here. So your second point will fall here. Then 0 and 3. So 0 and 3 will fall here. Then 1 and 5 will fall somewhere here. And 2, 7 will fall somewhere here. So if we extend this one, no, your graph, no, will somehow will fall here. So your line, as you can see, your line rises from left to right, meaning to say that your m or your slope is a positive value in this case. As you can see here, no, your y is equal to 2x plus 3 as your function, where your 2 here, your positive 2 here, is your m or your slope. So that will be your slope. Following the pattern for your y-intercept form, slope-intercept form in your analytic geometry, no, that your 2 here is your slope. If that is a positive value, then your line rises from left to right. So at this point, let us investigate on the inverse function f raised to negative 1 of x is equal to x minus 3 over 2 by using the values, y values from the original function as x values of the inverse function. Observe the same process in completing the table of values by substituting the x values to the given inverse function. Now the table of values will be as follows. So in this point, if you try to observe this table, this negative 1, 1, 3, 5, 7, these are y values in your original function. So in this inverse function, this will not be your f raised to negative 1 of f of x. So this will be the value of your x in your inverse function. So this will be your value or your computed values of your range, no, in your original function. Once we substitute those given values of x, no, from negative 2 to positive 2, then the computed values for y, no, in your original function is negative 1 to positive 7. Now, dealing with your inverse function, we just simply swap, no, or swapping of position or swapping of values between your x and y variables. So we interchange now your x and y values. So whatever your values of computed y, your computed y values in your original function, that will be now your x values in your inverse function. That we're going to substitute now in the values of as a value, of your variable x in the given inverse function. So for us to complete the y values, let us substitute each x value from the given inverse function, which is f raised to negative 1 of x is equal to x minus 3 over 2. Now, as you can see here, we just simply substitute negative 1, positive 3, positive 5, and positive 7 to our inverse function. So we just simply substitute this one, negative 1, to your variable x here. Then the resulting value is negative 4 and 2. If we simplify this one, this will be equal to negative 2. If x is negative 1, then your y is equal to negative 2. If we substitute positive 1 to your x variable in your given inverse function, that will be 1 minus 3 over 2, or negative 2 over 2, or simply equal to negative 1. So if x is 1, then your y now in your inverse function is negative 1. Same thing with your number 3. If x is 3 in your inverse function, then if we substitute this one, that will be 0 over 2, then your inverse function with respect to your 3 now is equal to 0. Therefore, if x in your inverse function is equal to 3, then your y is equal to 0. Then, if x is 5, if we substitute this 5 no, in your given inverse function, 5 minus 3, it's 2 over 2, that will be equal to positive 1. Therefore, if your x in your inverse function is equal to 5, then it's automatic that that your y now is equal to positive 1. It's the same thing with 7. No? It's 7 minus 3 here over 2. 7 minus 3, it's 4 over 2. That will be positive 2. Therefore, if x is equal to 7, your inverse function, then your y now is equal to positive 2. It's the same scenario, no? That's why if you try to observe our computed values here, that will be your negative 2, negative 1, 0, 1, and 2. These are the values of your x or your domain in your original function. That's why even if we don't need to check, no, or we just simply swap the positions of your values, it is still the same, no, with the values, no, of your original function. So we just simply swapping the position or values of your x and y, no, from your original function going to your inverse function. So whatever your domain, your original, that will be your range in your inverse function. So whatever your range in your original function, that will be your domain in your inverse function. In this case, no, these computed values of y is automatic your domain in your original function. So as you can see here, this will be your x value, not your f raised to negative 1 of x. This will be your x value, and this will be your y value in your inverse function. So if we try to graph using your Cartesian plane, your negative 1 and 2 will fall somewhere here. Will fall here. Negative 1 and negative 2. Next thing is positive 1 and negative 1. So your point will fall here. 3 and 0. So your third point will fall here. 5 and 1. So that your point will fall somewhere here. Then 7 and 2. So your last point using your 7 and 2 as your x and y coordinate, no? So this will be your 5 points, no? With respect to your table. So again, as you can see in this function, no, this is the graph of the inverse function f of negative f raised to negative 1 of x is equal now to x minus 3 of over 2, I mean, no. So as you can see, your m now, or your slope now, is a positive value. It's 1/2 x, meaning to say that your line rises from left to right. So as you can see, the behavior or the orientation of the line, once we connect these 5 points, no, if we plot these 5 points, no, using your x and y coordinates, no, with respect to your inverse function, and this graph will represent your inverse function, then your line rises from left to right. So if you try to observe this graph, no, this will be your graph in your original function. So this will be your graph in your inverse function. Now, this hidden line here, that will be your y is equal to x. So if that is your equation that will represent this hidden line, meaning to say that this hidden line will make 45 degrees from your x-axis here. It's the same thing with your y-axis here. No, so there is a 45 degrees also with this uh, in between your y and this hidden line. So as you observe, there is a diagonal line represented as broken line. So we represent this diagonal line as broken line across the origin of the point of intersection of the line f of x is equal to 2x plus 3 and f raised to negative 1 of x is equal to x minus 3 of 2. So however, for easy step, if you are asked to graph a function and its inverse, all you must do is graph the function and then switch all your x and y values. Yes, it is no. It's more on switching no your x and y values, or swapping of positions, or swapping of values no between your x and y values in each point to graph the inverse. Just look at all those values switching places from the f of x function to its inverse f raised to negative 1 of x and back again. Furthermore, the two graphs will be symmetric. So you need to take note of this. That this line and this line no, will be symmetric about the line, or about your diagonal line here, or your broken line that represented by broken line. So that's why if this is your broken diagonal line, no, these two graphs that represent your original function and your inverse function will be symmetric to this line. When you say from this point of intersection, so each point here that will fall in your line, in your inverse function, and each point here, there is a corresponding distance no from your diagonal line here. So that will be equal. So whatever your point here and distance from your from your original and your inverse function, they are equal, no? The distance from any point, no, to each corresponding point to your original function going to your inverse function, it's the same distance away from your diagonal line, or represented as broken line. So for your activity, so give the table of values of each of the following functions. So show your solution. You need to show your solution. Use negative 2 to 2 or positive 2 as a value of your x, no, in your original function. So these given functions are original functions. So what you need to do is to substitute negative 2 to 2 for you to get the value of y, then swapping or switching of value switching of x and y values for you to get the coordinates of the point that will represent no your line that will represent again your inverse function. So that will be your task for this module 13 under your general mathematics. Thanks for watching. Please like, comment, and share, and subscribe.